Okay, in this problem, it is a problem. Actually, if you look at it, you're on a design team for a water slide, and this is the design that's been suggested: a 30-meter high leg here, 40 meters here, and then this slide here. This would be water. Now it's a water slide, so kind of some of the things that you might guess about a water slide is there's very little friction. And of course, you know, if you sit here, you're going to be pulled down the slide by the force of gravity. So one of the questions they're asking about is, you know, what's going to happen? In theory, how long will it take for you to get to the bottom? Presuming that there's negligible friction, how fast would you be moving in the direction of the slide when you got to the bottom? So this is a question about the speed or velocity in the direction of the slide. And you had a camera, and we're taking time snapshots of the location of the person on the slide. And the question is, where is the person after, you know, 1 second, after 2 seconds, 3 seconds, and put those pictures here. So, and then the last thing, convert the speed at 1 second to miles per hour. So let's go ahead and start in on this. So how, in theory, how long will it take? Well, we know theoretically the only force that's pulling on this person here is the force of gravity, and we know that gravity pulls towards the earth. Of course, that pull toward the earth can be broken up because of the principle of superposition into two pulls. It could be broken up into a pull in this direction and a pull in that direction to equal a pull in this direction. So it's going to be this acceleration due to gravity here, and there's going to be a component in this direction, and perpendicular to that, a component in that direction. So the thing to notice in this, when you draw these things, of course, is that gravity is the hypotenuse. Gravity is the biggest one that is, you know, you're not going to have, you know, you can draw this mistakenly. You can draw it this way. You can draw a set of vectors that looks like this, right? And then like this, and like that. So, however, it's what you can see when you draw it this way is that the biggest one is this one here. And you have to ask yourself, well, wait a minute, could gravity, could this pull be bigger than the force of gravity? And does it make sense that gravity acts sideways? Well, probably not. You know that it's probably not bigger than gravity unless you got somebody else pushing on it, an acceleration also adding to the gravity. But you don't. You just have gravity by itself. You're just sitting here from a dead stop and you're sliding down. So the relevant vectors that you would draw are the ones in red here. So let me see. Can I actually even erase these? Let's see if I can do that. Okay. Is there such a thing as an eraser here? Pen tip. Oh, here it is. Eraser. Oh, no, it doesn't work. All right. Okay, I'm starting from a clean drawing here. So I've got the acceleration due to gravity. Acceleration due to gravity here. And we're using 10 meters per second squared. 10 meters per second squared. And I've got that broken into two components. One like this, and then at 90 degrees to that, one like that. So the one we're actually really interested in is the one that's in the direction of the slide, because that's the one that causes the velocity to increase as that person goes down here. So how big is that? Well, let's draw the triangle. We need to draw a similar triangle. We know this is 30 and this is 40. Now, you might recognize this special triangle, this right triangle, is as a 3, 4, 5 right triangle, which you will see a lot in problems. They will just kind of use this one because people are familiar with it. So that means this is 30 meters, this is 40 meters, this is 50 meters. So which angles are similar here? Well, I know that if we were to draw this acceleration vector here, and then this one, and this one is analogous to this one because it's the hypotenuse. The 90-degree angle is here, so that means that the 30-degree angle, it means the 30 leg is similar to this one here. and the 40 is similar to this one. Now you may say to yourself, well, how do you know that? Well, actually, let's do it this way. I'll really amplify it. I'll make the triangle like this. You know, so it's, you can kind of the angles are harder to or easier to differentiate. So you've got the 90 here. So you know now that if acceleration were acting like this angle, it would be like that. So you can see now that this smaller angle is the same as this one. So in the same case, this angle here, the one down, is the same as this one. So this angle is the same as that one. Therefore, 50 is like the as the acceleration due to gravity. Now again, this one here, so you see 50, 40 is the one next to that angle. That means this one is like, that means this one, this side is like this side. 50, the angle, 40. 50, the angle, 40. So that means this leftover leg is the same as this one here. Or, I don't mean the same, I mean similar. So if we were to, you know that similar triangles, you can set up a ratio. You can say 50 is to 30 as the acceleration due to gravity. 50 is to 30 as the acceleration due to gravity is to whatever that is. Is to the acceleration in the the direction down the triangle. I'll indicate it like that. We know this is 10. This value is 10 meters per second squared. So we can solve for A down the triangle is equal to, multiply these two like this and divide it by that. So I have 30 times 10 meters per second squared divided by 50. So that is 30 divided by 5 is equal to 6 meters per second squared is the acceleration down the slide in this direction. So we've got that is 6 meters per second squared. And the question was, how long does it take to get to the bottom? And we know that the velocity, let me just go ahead and put an axis system on this. We know that the velocity, if we are tracking this as our, let's call that the x direction, we know that the velocity, this doesn't help us, this equation, velocity initial plus at, because we're, well, we know the acceleration, we don't know the final velocity, so we do know the distance of this thing, x final equals x initial plus v initial t plus a over 2 t squared. We know that the initial distance is 0, x equals 0. We know the initial velocity is 0, and we know the acceleration here is, 6 meters per second squared. So the final distance, 50 meters, equals 6 meters per second squared divided by 2 times t squared. Or in other words, 50, this is 3, 6 over 2 is 3 t squared, so we've got, let me go over here, t squared equals 50 over 3, 50 meters over 3 meters per second squared. And what I find here is the meters cancel and the second squared comes up, so that we have 50 over 3. What is that? That's about 17, is that right? 7 times 320, yeah, that's about 51. So it's about 17 second squared equals t squared. So we take the square root of this and we get that t is equal to the square root of 17 seconds. That's a little bit more than 4, because 4 squared is 16. So we only have one significant figure, so we're going to just call that 4 seconds. So we did it. The time it takes to get to the bottom, How long will it take? It is about 4 seconds.